Hello. Okay, so I'm back for part 2 of a video on using periodic functions to determine primes, composites, and factors. And basically just talking about the prime numbers and functions that you can use to play around with them and determine them and manipulate them and do things like that. I made an hour and 15-minute video was the first part. The first part just explained the general technique, which is how do you take a periodic function, turn it into something that tells you the number of factors of a number, and then how do you turn that into prime counting functions or prime generating functions from there. This video is for people who really like big equations and prime numbers and heavy math at some level. A lot of these equations are not 100% computationally friendly, but they are 100% deterministic, and they provide a lot of forms and primality checks and things that people haven't seen before. And so I'm going to pick up here with a part 2. And the second half of this paper talks about, now, once you understand the general technique and what's going on, the second part of this paper talks about, well, what else can you change to try to make it simpler? Or what other ideas can you come up using those techniques? Or what other functions serve the same forms? Or what other periodic functions can you use? And so forth and so on and things like that to come up with other forms for the primes. And so we're going to go with that. And now this next section, and there's some really neat formulas in this part and some things that people haven't seen before. And most people haven't seen before. And there's something in this section which I really am happy with. And it's where we're going to start off with these things that I labeled or call product polynomials. And in my years exploring the primes or certain functions related to them, that was years ago, and I can't think of exactly where now, but people, maybe Math Stack Exchange and a few other places, people come up with this idea that they think there should be this polynomial function that behaves a certain way with roots, and yet you never see it anywhere. And here I'm going to talk about this function that people have an intuition that it's out there, but it hasn't quite been worked out, or it's not as common to see. And I call it product polynomials. And it's using polynomials periodically is basically what it is, and we're going to get into that. And so let's just jump right in here. So I say one useful form for generating these periodic functions is something I often call a product polynomial. What are they? So it's commonly known how to generate a polynomial with any desired root, simply by multiplying out the quantities of x minus root sub n, where the r sub n are the roots. So for example, if I have a parabola or something, and I have x minus 3 times x plus 4, we think of the minus 3 and the plus 4 as the roots, or the opposite of those numbers, if you want to think about it that way, because it equals 0. X minus 3 equals 0, x equals 3, and x plus 4 equals 0, x equals minus 4. That kind of thing. So those are the roots to that polynomial, and they equal 0 at that point, right? But what if we took all those roots and made them the multiples of a number, creating an infinite polynomial with periodic roots? See, and likewise, taking all the multiples within a given domain creates a function with periodic roots, at least over that domain. So this is useful for 2 reasons. One, we can now use polynomials instead of our trig functions at the beginning. The goal is to do this whole process with different starting periodic functions and find one that has a closed form in the end result. So instead of using our cosine function as our periodic function, now we're going to use a polynomial as our periodic function. And how do we do that? Also, and I talk about here, the other nice thing of this is that the multiplication of a finite number of integer roots and the resulting polynomial are purely algebraic. So there's no trig involved in this version. It's all just multiplying, adding, subtracting. It's all just arithmetic. Purely algebraic, using only the basic operations of adding, subtracting, and multiplying. This shows that all the techniques described in this paper can be carried out using a polynomial having a finite number of terms. So I often say this too. It's commonly known, and if you look up for on Wikipedia, for example, functions for the primes. It's known that there's no polynomial function that generates all the primes. That's something easy enough to prove, and you can say, oh, there's no polynomial function that generates all the primes. However, there's a family of polynomial functions that generates all the primes. So it's not a single polynomial function that generates all the prime. That doesn't exist. But there's a family of them where if you learn how to write down the whole family, capturing the family of those polynomials captures all the primes. And that's what we're going to do here. So now again, of course, this is often ended up with a big clunky polynomial, some giant thing, algebraic thing you're calculating, but it's finite nonetheless. And you could even go further and use this full infinite domain to represent the entire distribution or recursive sequence for the nth prime. So again, I'm showing that even though some of these are really unwieldy or not computationally friendly, you can start with just polynomials, or what technically turns out to be a family of polynomials, and in a finite number of steps, generate a finite polynomial that will calculate you the nth prime or a prime of any size, or know the number of primes less than a number. And this is a starting point for people to go from there and learn some of these techniques. So we're going to consider the following form. I call it R of X here. So we've got this product. This is just a regular product function here. Now we're not using this big pi to be the pi counting function, even though that's typically what they use too. Here I do mean the product function. That's why these are called product polynomials. So imagine here I've got x minus k times n. K is going to be our wave number like before. So let's just say, like, I'm thinking of to help you make the visual gap in your head. Imagine the cosine wave where our wave number was 2 and it hit all the peaks, 2, 4, 6, 8. It's just a wave going up and down between the values of -1 and 1. But all its peaks are at 2, 4, 6, 8, 10, 12, so on. The 2 wave, the wave number of 2. Okay, that's periodic and that's got a wave number of 2. So if we want k to be 2 here, k is our wave number, we'd have x minus 2 times the number n, right? But n is going to be our index for our product function here. So basically we have x times 1 times 2, 2 times 2, 3 times 2, 4 times 2. Or in other words, we have what this is saying for our 2 wave is we have x minus 2, x minus 4, x minus 6, x minus 8, x minus 10, and so forth. So if you were to think of that as a polynomial and you multiplied that out, you would have roots at 2, 4, 6, 8, 10, all the even numbers, and so on. So what we're doing is we're creating a polynomial that is periodic within our domain or our range. Again, we could run it over all infinity and have all those periods. But we're generating a polynomial that has all the roots as our period. And that's what you're seeing here in this x minus k times n. So the product represents and generates all the roots between 0 and k times however far you run it. That's your range, your domain, however you want to think of it that way. And as a note here, I point out that this function has 2 other alternate representations into forms that people are familiar with some of these other functions in terms. For example, I can write this R of X, that's just as straightforward as it is here. You can write it like this or like this. And in these equations, in this 13 here, this is minus k to the b times this 1 minus x over k sub b. And the b in the subscript is Pochhammer rising factorial. So this part here means the rising factorial, which is, if you're familiar with math, you know what the rising factorial is. Excuse me for a minute, I got a bit of a cough. I apologize. My throat's dry from doing the first one. I should probably have taken a break, but we're just going to plow through some of these. I wanted to make another video. So this you could write as this minus kb times rising factorial, or it's also equal to this in terms of the gamma function. So minus k to the b times gamma of this over gamma of this. So here's here's the function and two other representations for it in things that are not products. They're just in this term. Okay, great. So now we have this thing that we're turning into a periodic polynomial, or this what I call these product polynomials. So here I have a picture of it, and for example, here's the first 8 roots of the k equals 3 wave. So we made our wavelength 3, or our period 3, I should say. So k is 3. So here you see k is 3. And I just ran it up to 8 just for an example. And you can see it generates all the roots at 3, 6, 9, 12. And when you multiply this out, of course, in between the roots, the polynomial grows and shrinks so big and so fast that I say here the curves in this function are far outside of the little snapshot here. I would have had to show way up the page, up to hundreds or thousands or whatever to show where this red line goes up and comes back down, and goes under and comes back up. But you could plot this and see that it's just a polynomial with all those roots because, well, we defined it to have those roots. So now we're building this periodic polynomial here of the form x minus k to the n. Okay, great. So now we have to do some shifting and some crafty part like we did before just to get the information that we want at these integers. So instead of adding the absolute value this time, we're going to take the square of the function. So by squaring it, the zeros, the roots still stay roots, they stay 0. But everything else, all the negatives become, squared and positive, and all the positives become squared, and everything gets bigger. Great. But just like before, now we have this function that's all positive because we flipped it by squaring it, in a sense. Or we didn't flip it, but we squared it and brought all the stuff under the axis up. But you'll have all these things that dip down and touch 0 right at the root. Well, that's kind of like an upside down wave. So we're going to take the negative to flip it over just like we did before, and then shift the function up by 1. So now we've set all those roots that were 0 up to a value of 1. And the result is now a periodic function within that domain with all the peaks set to 1. Or again, it's not purely periodic, it acts periodic, if you want to think about it that way, within that region. And here's what that looks like. So now once we have that, that can act just like our cosine wave did originally. So the peaks are very sharp and narrow here, so they appear like a spike or a comb. But it's actually, if you were to zoom in, you'd see the curve, of course, of the peak. But here's what you get. And so we take this, here's the function we started with, our x minus k of n, where k was 3 and all that. And for the example, we squared it. Here you can see it's squared. We flipped it over with the negative after we squared it, and then we raised it up by 1. And now you're left with this quote-unquote periodic product polynomial, where I've got the value at 3 is 1, the value at 6 is 1, the value at 9 is 1, the value at 12 is 1, and so forth and so on. All your values at your wavelength k will be 1. Great. So you could now go back and plug this function in green here. You could plug that in instead of cosine of 2 pi x over k. You could use this instead. Now, of course, you'll have a sum of these product functions and stuff, but I'm showing you that you can do this with any periodic function, and that each one changes the result that you get. Some are more easy to calculate than others, and the holy grail of what we're looking for is a closed form for one of these. But this is another interesting one that comes about when you start playing with these stuff. So applying the results to f of x as suggested produces the following. So now, instead of having to, again, each one you have to learn what the visual graph is doing to know how you have to shift it or flop it or alter or absolute value or whatever. But in this case, because of the nature of the function that we had, you have to do this process and then add the absolute value to itself, and that's it. and then scale by 2. You don't have to shift the same way that you did the other one, but you end up with this function. So now this function 15 here is an alternate version of our f of x from way back in the previous video. You'll see where I talked about the number fact function. Well, here it is again, and that produces this alternate version, and this is a equal number fact function. So that's a pretty interesting form that you get to count the number of factors of a number. And you can do it just with this. Where again, all you have to do is run b as high as you need to, check. Same with x. But this is the basic way to use a different function and use these things called product polynomials, which is kind of an interesting way to go about it. And again, the reason I like that is because now instead of those trig functions, because the sums are only have to get written up to x, you could calculate this out. You could write this out and it would just be a big polynomial. And this is the family of polynomials I was talking about. And when you go through that other process with the g of x and the h of x, you'll just get a giant polynomial, but that polynomial will be valid up to wherever you set it at. And you can make a polynomial as big as you need that calculates it for all things up into that value. And it's kind of interesting that this form will show you all of that. And so, well, it's just kind of interesting. And you get this giant polynomial that tells you all the primes. So now we're going to talk about more of these alternate functions like this one and what other things can you do. Cat just hopped up on the desk, so you might hear him squeak. Hi, buddy. So it's been mentioned that these techniques can be done with other periodic functions as the base. Throughout the development of the methodology, I've explored a lot of these, many alternatives, usually looking for something that could simplify in the summation. That's the ultimate goal, is to find something that does this technique and yet also has a closed form or simplifies. That would be a major breakthrough. So that would lead to profound results, is what I say here. While I've not found that magic function, that's the holy grail that everyone's looking for, the so-called closed form of the primes, I have described here how you can go about finding it and a realm in which it could live. If you can find a function that meets these requirements and also has a closed form, you'll have a holy grail for the primes. And so in my search for some of those and trying different things to look for stuff that simplifies, I've come across some unique or interesting observations and equations and forms that people have that aren't really like readily available in textbooks, but are kind of neat and are related to all this stuff. So one thing that you can try to do in the beginning is replace the trig functions. Sums of trig functions often don't condense, and if you can find a way to find one that does, that's great, or work with them, great. But let's say we just try stuff like we did with this product polynomial to get rid of trig functions in the beginning. It is possible to get rid of the trig functions added during the wave peak restricting and renormalizing phases, and to exchange them for exponential power functions. The idea being that in order to avoid the noise during summation, when the function slid down, the peaks must not be wider than 1. I mentioned that in the previous video. And that the amount is also based on the wave number. One such valid option is shifting them down by 1 over 1 to the 2k, and doing so results in the following. So what I've done here is this. So in our original function in video 1, we started with a function that was trig, and we shifted it down by an amount that was trig, and then we went on from there. This one doesn't get rid of both of the trig functions, but it gets rid of the shifting down by a trig function part. I realized there was another, I could at least get rid of that trig part by shifting it down by another amount that met the requirements. So if you go watch part 1, you can see what those requirements were in that part. But I realized that this 1 minus 1 over 2 to the k met the requirements, And so we've gotten rid of some of the trig functions in this version. Again, we're looking for anything that can simplify it. So here is yet another version, we're going to have a bunch of these now, of these f of x's that you could go back and play with and mess around with and replace the trig function. So here you'll see our 2k, or cosine of 2 pi x over k still, but instead of that minus another trig function, now it's minus 1, and then plus a 1 here. And so, and this 2 over k, this 2 to the k over front. So when you do all the simplification, this is what you get. And so this is another version of that f of x that's a little bit simpler, because it doesn't have trig function minus trig function. It just has some other numbers in here and a 2 to the k. So this is a little cleaner. And you can start to determine which one of these are more computationally friendly and how many steps does it save you and so forth and so on. And here's that graph just to show you what it looked like a little different. But again, you can see this familiar pattern where all the primes are equal to 1. So 2 is 1, 3 is 1, but 4 is equal to 2, the number of factors, 5 is 1, 6 is equal to 3, 7 is 1, 8 is number of factors, 9 is number of factors, 10 is number of factors, oh look, 11 is 1, and so forth and so on. So here's another version of that number factor function, the counting of number of factors function, but we slid it down by a different amount, and we used a little different trick in our flip-flopping and everything, and this is what you end up with. So we got rid of some of the trig functions in this version. And that meets the requirements. The difference in this version is that the wave peaks do not all have the same width, because the wave number and the power. So you can see that the shapes start to change and these peaks get very, very thin in this version. And every version has pros and cons, but okay. Yet this function seems at a first glance to be slightly simpler and therefore more computationally efficient. So this is just showing you that different things can affect the computational efficiency, and we're trying to find ones that ultimately simplify it or play around with it and see where this method has flexibility. So the trig functions were used as the periodic specifically to eliminate use of logic functions like ceiling and floor. So like I mentioned in the first video, the goal when coming up with a prime function is technically you don't want it to be an algorithm. You don't want to use floors or ceiling functions because those are not pure arithmetic functions. They're considered logic functions. However, because of how commonly they come up and because I was playing around with different things that could act as periodic functions and trying different formulas, I realized that there was some stuff you could do with floors and ceilings that, again, from that perspective of, is it just a function or an arithmetic function? No, it's a logic function at that point, if you want to get real technical. But some of those are still more computationally efficient, depending on how your thing calculates floors and ceilings or handles those exceptions or whatnot. So I mentioned some of them here just to show, again, different examples. And in a sense, this is more like a Willens formula at that point, like I mentioned in the first video. However, for example, it's entirely possible to devise a periodic function, say, using only ceilings. Of course, you could make it with floors, too, if you had to. And with no trig whatsoever. So if you look at this function here, and you play around with it, this is a periodic function using ceilings. And just the wave number k. And this thing is kind of simple here, the 17. It's a neat little function that it acts periodic in a period of k. And when you use this periodic function and apply the rules to your number fact function like we designed it in the first place, you get this version right here. So here's a neat version with just ceilings that acts as the number of factors of the number. And there it is. And again, you can see that trick where you take the thing and you add the absolute value of itself. That we're still using that absolute value trick in this version, where we've taken something periodic, we've scaled it with our 1/2 out here to change the amplitude back. And here I plotted it just to show you what that looks like. So you can't see the whole function here, but that's this here plotted. And you can see because of the ceiling, it does these weird lines like it would like a step function. But those values are still, for 2 it's 1, for 3 it's 1, for 4 it's 2, for 5 it's 1, for 6 it's 3, so forth and so on. All the primes are 1, and all the other numbers are the number of factors minus 1, not the number 1 itself. You could always shift it back up 1 or do whatever you need to run it to get, add 1 to that. But here's another version of that number fact function. And from there, everything else can be built using this version. So that tells you the number of factors of the number, and that's a neat representation without any trig. But alas, we've used logical functions here and not purely arithmetic ones. Okay, here's another version using factorials. Now this one's pretty interesting because this is no trig and no ceiling or floor. So this one's a bit odd computationally, and I talk about that here. But here's a version just using the factorial function of your number fact function. And this one turns out to be a bit odd in that it will call, so when programs are designed to run this and they want to know how to handle these factorials, like if you try it in Desmos or something, it will call the gamma function for calculation of the negative factorials, because sometimes these values in here end up being negative and you get a negative factorial. And it relies on the program used to ignore does not exist calculations when gamma of a negative integer is called. So the program has to realize it has to be set to say ignore does not exist when gamma of negative is called and just spit out everything else. So if the program doesn't fault when it gets that does not exist and it just ignores it, you'll get the correct answer. But again, that was something else that had to be considered, but it doesn't have any trig functions and it doesn't have any logical functions. It's only arithmetic. So here's another neat example. And the benefit to this one, as I said, is it has ridiculously tight and narrow wave spikes. So much so that the graphing program already starts to truncate the width to 0 by around x equals 5. Unless you zoom in, prompting it to use more precision. And it just shows options provided by this technique, where you can come up with these different forms that all have pros and cons, but all using the same method and to generate the number of factors of a number and the primes. So here it is. Here's this thing plotted. And Desmos can plot it. Again, it's calling the gamma function, but it properly handles the does not exist of the negative things, and I guess it just ignores them. And you'll notice here, though, 2 equals 1, 3 equals 1, 4 equals 2. But here's what I said. These peaks become so tight, so fast. Like here it's kind of wide, and then it gets thinner, and here it gets thin, but up here it's super thin. And you saw that the 6 one showed up, and it's super thin. But the 5 one doesn't show up on this picture I have, but it does if you zoom in enough. There's actually a peak here that goes up to 1. It's just so thin and so tight, it doesn't even show up on this graph. You just get these peaks that are like fractions of fractions of a number width, but that shoot up to 1 at the proper value where there's a prime. And again, I just do this to show some examples of and some neat formulas that you wouldn't see elsewhere. And different versions. Okay. So that was replacing the periodic function, if you will, and the trig functions, and trying to come up with versions that didn't use trig functions. Okay. But part of the technique is that absolute value part where we always take we add a copy of the absolute value of the thing to itself and then adjust by half for the amplitude. So there are some versions that I found where, for example, I couldn't get rid of the trig functions. I had to still use trig functions, but I was able to completely get rid of the absolute value part. And I found a different way to flip-flop it and get that same information out of the zeros and the ones above the right integers and all that, which is what we did in the first video. So another approach is where we're looking for a reducible sum ultimately, but we try to replace the absolute values. The simplest way to do that is to use the square root of the square. You can think of an absolute value as the square root of the square where you're only taking the principal root. And that's allowed if you want to go that way. However, when doing so, it's important to only use the traditional positive roots or principal roots for valuation. And if a program mistakenly sees the square of the square root of the square, and it just says, "Oh, I'll just take that thing," then it's going to get it wrong. It has to actually do out the calculation and then take the square root. It doesn't make the mistake of symbolically combining it and then just canceling out the numerator to 0. It wouldn't make any sense. But in any case, there are some techniques and methods that I came up with to avoid the absolute value. And one of the most beautiful and concise examples I found was this. This, in the grand scheme of things, this is a fairly simple sum. And this replaces that whole number fact function with just right here. No adding copies of the absolute value and adjusting and this and that. This right here is the number fact function, where you take the sine squared over the wave number squared times the sine of the wave number version squared. And you get this. And here again, you'll see 2 is 1. Now, it looks just like a wave, but 2 is 1, 3 is 1, 4 is 2, 5 is 1, 6 is 3, 7 is 1, 8 is 3, 9 is 2, so forth and so on. 10, 11 drops back down to 1. All the primes are 1. And all the other values that they're integers are the number of factors of that number. So this is a really interesting one. That this sum here is the number of factors of a number sum. And no one's really, you don't really see that in a book for just a formula for the number of factors of a number. Well, there it is. This f of x is a formula for the number of factors of a number. And that's a kind of a unique and concise sum that you wouldn't have seen before, and what it does and why and how it does it. But there it is. So you could use that as your starting point for a number of factor function and calculate primes and everything from it. Or if you could find the closed form of that sum, you'd be in some really interesting territory at that point. And interestingly, I noticed this version also acts as an extremely good bound for the original f of x. So here's this version of f of x, and here is with our very original one from paper 1. Just to show you side by side. So the original version was with all those waves and the absolute value stuff that we did. And of course, all the values have to be the same at the integers, and there they are. And so, just as a comparison. So, and I say here, an almost identical, version graphically, yet much more complicated, is generated using that product function. And it's mentioned as a contribution towards the study of equivalent forms. So this is just another one that I had come across at one point that I found very interesting. And I put it in here just to show other examples of how you can combine these parts or techniques. And this wasn't the product polynomial. This is a product function with waves. So this is using a product of waves in a sum. And when you do, here's another version of this number fact function. So then we looked at trying to replace the trig function. We looked at trying to do it without absolute values. And here I talk about replacing other parts of the technique that we talked about in the first video. The g of x, the h of x, and some of the other tests and things that you can do with this. So there are numerous ways to shift, flip, or flop the periodic functions during the g of x and h of x stage. That was what I called the flip-flopping stage in the first video. Some of these notable alternative transformations are included in the appendix, as well as additional primality tests, which I discuss here. Or I guess I just discussed those in the appendix, so I'll probably come back to that at the end. But there was some other little things that I had noted as I was going along. But next I jumped to something that I called prime waves and quasi-periodicity. And what did I mean by that? Again, I was just trying to come up with a term to talk about it. And this is just kind of for mental consideration or off the cuff a bit. But what do I mean by a prime wave or quasi-periodicity? So in one sense, you don't think of the primes as periodic because they're primes. They are things that aren't of any multiples of other factors of numbers and integers and stuff like that. We think of them as being the opposite of periodic in one thing. They're just kind of strewn between all the numbers and whatnot. However, the primes are all integers. And again, this is really hand-wavy at this point for this. But you could kinda, and I'm saying it loosely, you can kinda think as the integers as being periodic among the reals. Or at least they're very uniform and they act at a common unit interval, right? And so the primes, being all integers among the reals, are kind of periodic. Again, I'm using this very loosely here, but this is what I mean by the fact that you realize there's this connection between the fact that they occur during integers, which are periodic among the reals, if you want to think about it that way, but more so that the sieve of Eratosthenes, or the sieve technique that we're using in a sense, the primes kind of are periodic in their nature, meaning you're taking out all copies of 2 of a number except 2 itself. You're taking out all copies of 3 of a number except 3 itself. You're taking out all copies of 4 of a number except 4 itself. And of course, 4 is already taken out by 2. It's redundant. But it doesn't change the fact that there is kind of that periodic nature to what you're removing to then leave the primes. So it goes in number and set theory, you get into stuff like, I don't remember it exactly, it's been 20 years, but you get stuff like, the image of a periodic set of integers is periodic or something, where like, if you have something periodic, but you take all the integers and you minus the periodic thing, what you're left with is still periodic. It was some rule in set theory. And it's stuff like that. So that's all I mean when I say prime wave or quasi-periodicity. It's that I'm noticing that there is some kind of periodic nature to the primes. Or indeed, in this case of this technique that I've used, we've built all the primes and the number of factors of a number and everything off of sums of periodic functions. So it's like a big wave. It's kind of like a periodic wave, that you built. That's all I mean by this section. But you can kind of take this concept further to conceive the idea of quote-unquote primal frequency or primal period. By definition, the idea of periodicity is based around something that constant or repeats. Simple waves have a fixed period, right? However, as soon as you examine things like forced dampened waves or dispersion and Doppler effects, ideas like variable frequency and modulation, come up. A question arises. If you plug something, so you have a wave and it's periodic, right? Well, what happens if you plug something non-periodic into the period of a wave function? Is the overall thing still periodic? You kind of get into this weird type of logic. From the standpoint of it still being a wave, it's this oxymoronic non-periodic period. You just said I'm plugging something non-periodic into the period. But that's like a paradox. You've created this non-periodic period. What does that mean? It could be considered periodic from the sense that you're plugging it into the waveform. It's periodic. That is, whatever you plugged in is literally periodic. From the other standpoint, though, it's not periodic, as it displays no simple repetition. And this will dissolve into topics like chaos theory or what constitutes a pattern or chaos. However, even the most chaotic pattern, note the oxymoron again, quote-unquote chaotic pattern, can be considered a pattern if one labels it the de facto name of said pattern. So you get into some kind of strange loop, paradoxical, ad absurdum logic, where the pattern of all the sand on the beach is the pattern of all the sand on the beach. It's not really a pattern, but it's pattern, if you will. And so again, I feel like the primes kind of fit that category. They are kind of like the least periodic thing, but they're still periodic. They've got primal periodicity, or something weird like that. So where did I go from here? I'm just reading for a second to see if I really want to talk about this or just skip towards the end. So here I started to talk about, I don't really want to talk about this at the moment, but this is just more me kind of waxing philosophic about this idea, and that so that there's this point where you reach the h of x equation and the composite wave at that point has a value of 1 for all composites and 0 for all the primes. And it's of particular interest then to swap all the values, resulting in the prime wave, with the primes having a value of 1 and the composites having a value of 0. So the easiest way, there's numerous ways to do that. Probably the most direct way is to run it through a linear transformation of y equals minus x to the 1. It's just taking all the 1s to 0s and all the 0s to 1. And so here you see the h of x from part 1 of this video, and I've just run it through this linear filter, minus x plus 1, minus h of x plus 1. And now if you look at this thing here, this was our composite wave from before, where all the composites were 1, where all the primes were 0. But now all the primes, and except for 1 here, we're ignoring this number 1, but all the primes are 1, 2 is 1, 3 is 1. Oh, but composite 4 is 0. 5 is 1, but composite 6 is 0. 7, prime is 1, but composite 8, 9, and 10 are 0. All we've done is we've done a linear transformation on our h of x function to swap all the 0s and 1s. And so now we have a prime wave. This is our prime wave, if you will, where all the prime values are 1 and everything else is a 0. So again, this is this idea of quasi-periodicity or primal periodicity, or what I mean by the prime period, And I was just thinking about these concepts, and so that's what I'm describing here. The only concern here may be the resulting quote-unquote wave has plateaus for the prime peaks instead of curves, and all the composites are in valleys. But still, this works fine if you're just interested in those integer values, and one could take a summation over this prime wave to get the prime counting function. So you could have taken our h of x at this point, put it through this linear filter, and then just summed it, and you'll get your number of primes less than or equal to a number again. Or if you wanted, you could sculpt these plateaus to look like a wave again. There's ways to do that. But you're just complicating things. But you could. The point is to show that you could. And what I meant by all this. So another prime wave construction is the following, which results in some nice wave peaks for the primed and quote-unquote fanged valleys for the composites. So here was our original f of x, or any f of x, because any of them that I said meets that requirement you can use as your f of x in this technique. But if you do this other version of flip-flopping, which is kind of like the absolute value thing, but you can see it's like a double-nested absolute value here. However, it was another technique just to swap the 0s and 1s in the composite wave. And you're left with this thing here, which creates all these peaks of 1 at the primes and all these fanged valleys, which technically equal 0 at the integer at the composites. So this was another way to get this prime wave. I don't show it here, but an almost identical fanged version is this here. So this was another technique to do this, where we just found another way to do it with 2s instead of these 1s and minuses and stuff. And again, you'd have to play with these graphically to see why it works. But we're still following the rules that we said in part 1, where we flip-flop stuff a certain way. And you're left with this, something that looks like this almost identically if you were to graph it. And these are prime waves. They're just the prime wave. And then finally I say here's a completely sculpted version using an adopted h of x. It includes 1 as a prime. Again, there's ways to get rid of that, but they often complicate everything that much more. But you could remove it if you want with a little bit of adaptation. But so if you went back to the original paper, you could use any f of x you want, or the original one. You get to your g of x stage. The g of x turns into h of x. But instead of that h of x we originally used, here's another one. You use this h of x here, which was another way to just do what we did in those papers and meet the requirements of what information we were trying to save and extract and adapt. And then you create your new prime wave p of x here off of this h of x, which is just this version of it, 2 times it plus the absolute value of itself. And I do that just to show that if you take the time to play with these things a little bit, you can get some really nice clean waves and do everything. But here it is. People want a function that plots all the primes, or to say, well, what's the prime wave? Here it is. Here's if you go through those steps, like I said, you'd have a prime wave that is literally a wave of 1 and with the same, kind of peaks all at the prime numbers 2, 3, 5, 7, 11, 13, 17, 19, so on. And all the other composites are 0, and it's 0 everywhere else. So this is just the prime wave. So, and again, that's why I hand-wavingly say, okay, well, the primes are quasi-periodic, where you can make them behave construct them, like periodically, like a Fourier can, transform, if you will. Everything's periodic at that point. But that's what I mean by that. And we're almost done, and I'm going to make, my first few videos here have been very long for real math heads, an hour-long videos. I'm going to make a really short 2 or 3 minute video describing this thing that I'm going to show here in this next part, just to have a real quick video to talk about. But once you learn some of these techniques and you create these waves, you can use these to create twin prime and prime gap plotters and finders. So that number function, that number fact function, f of x, can also be used to plot, explore, and check for twin primes. Since primes are equal to 1 on that factor counting function, f of x, an easy application is then looking at f of x plus f of x at 2 further than it is equal to 2, which would show all twin pairs of the form x and x plus 2. So in that sense, if a number and 2 more than it are prime, i.e. a pair of twin primes, the only way that can happen with that number factor function is if you added those 2 values, you got 2, because only the primes are 1. And if one of those numbers wasn't prime, it's going to be greater than 2, meaning when you add it, you're going to get a number greater than 2. You're going to get 3, 4, 5, whatever. So if you take the number fact function and you add 2 values that are 2 apart, if they're equal to 2, you found a pair of twin primes. And if they're greater than 2, you know one of those is composite. But you can do some interesting things knowing that fact with those functions. So similar to the various constructions for functions of, like when we talk about the F stage, the G, the H, and the P stage, which we've gone through here, one can create more specific waves for the twin primes that are 1 at the twins and 0 everywhere else. These twin prime waves make it easy to visualize patterns of the twins, or any gap size. It doesn't have to be a gap of 2. It could be any size gap that you want to explore. So here, for example, in blue, I plotted that f of x plus 2. So now, wherever we get a value of 2, we know we're looking at the first of a twin pair. So example 3 is 2 because 3 and 5 are twin primes. 5 is 2 because 5 and 7 are twin primes. The next twin is 11 and 13. And 11 is 2 because 11 and 13 are twins. The next one is 17 and 19. And 17 is 2. So here we've made a function that plots all the twin primes. Now, I have a paper, which I'll eventually make a nice long hour or 2-hour video on or something, on proving the twin prime conjecture. Because there's a few problems that I deal with. I don't deal with like every unsolved problem, but my specialty happens to be primes, the Riemann hypothesis, and the twin primes, and a few things related to it. Like Mersenne primes and Fibonacci primes and stuff like that. But if you want to analytically prove there's infinite twins, I think I found a way to do that, and I have a whole paper written on it. However, I find like this is a very intuitive way to graphically show that there's an infinite number of twins. If you recognize these forms and recognize that these are infinite waves that oscillate infinitely, you can start to see. Now again, it doesn't quite show it, but I'm going to get into this more on this other little short video I'm going to make. But if you could somehow use this function to show that, say, for example, the derivative is equal to 0 an infinite number of times, then you would have proven the twin prime conjecture. All you have to do is show that there's an infinite number of values of this function here that equal 2, and you've got a check for infinite twin primes. And again, I'm not going to get into that too much here, and that's not actually how I go about proving it analytically, or my attempt at proving it analytically. However, here is something else that people could use as a tool to explore and or prove twin primes, or attempt to prove twin primes, or at least explore them and graph them. This graph right here, this technique will graph every twin that exists. Whether there are infinite or not, it will graph them all, and you can visually see each one whenever the function equals 2. At the integers, of course. And you can plot and find all the twins you want. So I talk about the same way we made prime waves before, we can make prime gap waves, which just are waves which gets rid of all this other extra information and just shows these parts here, where you want just the twins to appear. So here's a more complex option, but very clean visually, is to start with this function here, t of x, and then do this here, and you'll get the one below. So in equation 27, n is the gap size. Now all primes have an even gap except for primes with the difference and the number 2. Because all primes are odd except for the prime number 2, prime gaps come in the form of 2, 4, 6, 8, 10, so forth and so on, unless you're dealing with just the difference between a prime and the number 2. So in any case, for the twin primes, we're going to set the gap size equal to 2, because that's the twins. So in this formula here, you're setting n to 2. If you want to look at the gaps of 4, 6, 8, or whatever, you set that equal to n here, and you can plot it. And like I said, there are other versions, and I'm going to talk about one of them in a short video. But here it is. Here is what I just set up here without all the other extra information. And you can see when you set this to 2, it just plots the twins, where the peak represents the first of the twin pair. So here's a peak at 3, a peak at 5. The 3 is for the 3 and 5 pair. The 5 is for the 5 and 7 pair. Here's the next peak at 11 for 11 and 13. Here's the next peak at 17 for 17 and 19. Here's the next peak at 29 for 29 and 31, and so on. So you can just, this wave, this function right here, where t of x is this, and this is your plot, what you're plotting, that plots all the twin primes. You can look at them to your heart's content and just plot the twins. You want to see a graph of the twins? There they are. And so it's just the twin wave, the twin prime gap wave. So I find that that's pretty interesting, and some really neat forms here that come out of this for what are rather concise forms, even though some of them get computationally brutal. But here it is. Another thing that I designed out of this, now this is just kind of something I noticed along the way, and I thought it was really neat that once I was getting good at these techniques and flipping and flopping the waves and adding zeros and ones and all that stuff, I realized you can make something called an antipulse, or what I called an antipulse. So what is this last little bit that comes along with this paper? And what am I explaining here? When you think of a normal wave, you think of the pulses as the period of the wave. Like our 2 wave, the pulses were 2, 4, 6, 8, 10. You know, the 5 wave is 5, 10, 15, 20, 25, so on. And you think of a picture of a wave in your head, you think of the wave going up and down, and the pulses are the crests and the peaks, you know, the peaks and the crests, valleys and troughs and all that. Great. But we normally think of the pulse being in connection with the period. And we just think of the wave as going up and down in between, right? And what if we wanted the opposite? What if we had a wave that, like, was, instead of it being 1 at all the peaks, was 0 and 1 everywhere else? So it's kind of like this, it's you know, it's like an anti-pulse or an inverse pulse or something. So I described that here, and how do you get these and what do they look like? So while working with these functions in the prime gap finder, this thing up here and this t of x and stuff similar to it, I discovered that the t of x can be used to create this anti-pulse. Waves typically have crests and troughs spaced according to their wave number, with the body of the wave in between. But in the case of the waves developed in section 2, due to the absolute values, the body of the waves are 0 in between the pulses. Now consider the reverse. That is, a wave which is 0 where the pulses were, according to the wave number, but filled in with pulses in between. These antipulses, or I also call them valley waves, can be generated with the following formula, where k is the wave number. And I'm going to show one on the next page. So if you start with this t of x up here, that I use in this case, or something that meets the same requirements, you can do T of X minus this other version of this wave that we constructed, and K is the wave number of your antipulse. And I'll show you what that looks like here in a minute. So the example I'm going to show is for the K equals 3 antipulse. Now, in this example, there are still small fringe humps around the antipulse wave value. You'll see that. Yet the value at the integer will still be 0. And if you really want to get rid of those antipulse wave humps, you can just do the absolute value trick or square and a square root trick, and you can get rid of them too. It makes your equation more complicated, but graphically it'll be a pure, perfect looking antipulse wave. So here's what that looks like. So in the first version here is the, and you don't see the whole equation, but I described it on the page before. But here's the anti-3 pulse, the anti-pulse wave for K equals 3. So normally you'd have your values at 3, 6, 9, 12, so on. Here you can see that 3 is 0. And if you zoom in, you see these little bumps underneath, but then it comes back up to 0. But you can get rid of those too if you want. But the general idea is here you've got 0 at your wave number, 0 at 3, 0 at 6, 0 at 9, 0 at 12, and so on. However, all the numbers in between now have peaks of 1. So it's like you've subtracted your wave out of itself or something and just swapped where the peaks were and where the zeros were and stuff. And you get this really interesting kind of anti-wave or valley wave that has peaks at everything other than your wave number, but 0 at your wave number. And just to show the full example, here is putting it through the absolute value filter again to clean up those little humps. So for example, here's the 5 anti-pulse wave that has been cleaned up with more computation. So there's a pure anti-pulse wave that's 0 everywhere, peaks not at your wave number, but 0 at your wave number, which is just kind of odd. And again, you can make other constructions from here, but I thought that that was a unique way to make these anti-pulse waves. And lastly, in the paper, I had some questions about the technique that a lot of these questions I've answered for myself, or years later, they're not quite the same. I'm not going to go through all the questions in this paper, but a lot of the questions were just like, what time complexity space does it run in? You know, what other factor tags can you use? Stuff from the beginning of the first video. You know, how can you simplify things? Can you use this to test for Mersenne primes? Other things like that. But I was more interested in these two videos to show the technique of what's going on and some of the unique forms and formulas. A lot of this is just for people who really like formulas and want to see some of this methodology. And this concludes the general methods for using periodic functions and summation to create these formulas for the number of factors, specific factors, primes, nth prime, and so on. So then I go into the in appendix just to talk about a few other things or leave a few forms that I didn't put in the original paper. So in the original video, in the original paper, we take our f of x and we go through some stages for flipping and flopping for g of x and then h of x. But if you just want to look at all the flipping and flopping as what happened during that phase, here's what happens here. This is if you condense like the overall outcome of h of x in terms of f of x, this is what you did. Here was the full form. I mentioned this in the first paper. Here's the full form of the prime counting function when you expand it all out. And then I had mentioned that I was going to mention some other options on g and h of x in the appendix. That's all that this is at this point. So during that stage, I talk about flipping and flopping and how you go about it. So here was some other stuff that you could do with the f and g to get h instead of what we did. It still requires the absolute value in this case, but does not take as much other shifting, and it makes it more concise than the one I had used originally. Again, maybe the picture doesn't look as neat, but the data and the information that you're trying to extract is still there, or it changes the computational efficiency to make it easier. So I mentioned something here that I had noticed as another way to get an H of X rather than what I did in the first version, and what that changes and how it makes it look. It does one of these other fanged graphs. Another very similar version was this. So here was another technique that I had found. And again, they're all very similar methods of flipping and flopping just to get that information that you want. Hopefully somebody can come up with something even easier, but you have to understand the general technique before you can kind of explore it. And you can see what that looks like here. It starts to create this kind of thing. Same idea. We're just doing different flip-flops. And then at the very end here, I just threw in some other stuff without much explanation that I had found along the way. I've checked all of this stuff multiple times over the years. However, I think I did find that one of these in the appendix might not have been listed quite right. I'd have to go back through all of them. It's been years. It's been almost 12 years. But the subscript in these notations here is the rising factorial, the Pockhammer notation. So some of these I listed because they weren't as efficient calculation-wise for huge numbers, but they were very concise symbolically. And so, I put them down for just interest because of how concise they were for one reason or another. So a lot of these are quick primality tests that, again, aren't necessarily easy to calculate per se, but they're very concise forms of what act as primality tests or composite tests or whatever you want to think about it. So I'd have to verify all these last ones again, but most of them should be right. But for example, something like this, where you just take this product of this, this is again the rising factorial here, and the first one above I said is 0 when x is composite, and it's less than or equal, it's greater or less than 0 when it's prime. So this thing here, if you get a number, it's prime, and if you get 0, it's composite. Something like that. Weird little tests that I had found that worked for things. Here's one here where I believe, I'll say on the next page, but I believe it's greater than 0 when it's prime. Or if you get or 0, well, one or the other. It's either greater when it's composite or prime and 0 when it's the other. But I'll probably say here on the next page, let's see. By taking the square, it stays 0 when it's composite, but becomes greater than 0 when it's prime. Oh, so that was just an adaptation of this first one here where you square it and change the test. So, and I actually have other tests and stuff too, but I threw that in because that was just a concise form and something I had found at the time. I think maybe I got rid of the other ones that I wasn't so sure about, or didn't check the last time I went through it. So, in any case, that's it. I'll leave this as the second video. This has just been another long video about primes, counting functions, things like that. I mostly show this so that people can become familiar with the technique, for people who really like math and formulas, or want to see some of these unique ideas like the twin prime function, the primal wave functions, or these anti-pulses. And there's just some neat stuff that came up in exploring all this. And this is all based off of periodic functions. And the overall technique is how you can use any periodic function to create infinite number of prime counting functions, all of these different forms. And the real idea is to learn the technique, learn what's going on with how you go about doing some of these things, and then the idea is to find a function that maintains the requirements that are in this paper and yet has a closed form in the sum. If you can find a closed form sum that can either map to these forms or that has a closed form, that's when you're going to have the holy grail of that prime function that everybody's looking for. And there's some other ways I go about trying to calculate it and find one too. But this is something that people could work with and try to hone in this technique and improve it, or use it to explore and improve other things. And again, I provided a lot of functions in these papers which are not found anywhere else and are unique. And some of them have some pretty concise forms. So again, if you found any of this interesting, feel free. I only suspect very few people will get through all this or watch or listen, but if this is something that you're into and you find it interesting, feel free to leave a comment or reach out. But yeah, I just wanted to create some content and make some nice long videos for math heads and just kind of leave it up as a record of some of this stuff. The papers are out there. You can get them and read them. And again, I hope you guys found this interesting for the few people who really get into this stuff. And again, right now, I don't know that I'll do all math videos on this channel. I have a few other ones I could make. I could do a video, long ones like this about the twin primes. I have a short little video where I could do about 1 or 2 formulas. I'm going to make a short video about just the twin prime plotting formula, just because it's interesting and quick. A lot of what else I do is actually academic theory, having to do with topics and subjects of academia and how you teach and how they all relate to each other, and information theories and stuff. And so I might actually talk about that. It's not as math related. It's a total visual graphical thing. But I might make some videos about that stuff. But for now, I at least wanted to crank out some more math videos. And yeah, that's about it. I hope you enjoyed it. For anyone who gets through this much, thanks for listening. Leave a like, as they say, or feel free to leave some comments. And yeah, yay for the prime numbers. And hopefully we can kind of use this stuff to figure out other things with the primes. Or at least I hope I pointed out some aspects of it that people weren't as familiar with. And gave people other options of things to work with. So, all right, at that, I'll leave it. I hope you guys all have a great day or great night. And take care. Thanks. Bye.